it was in the email. I can't hear you. Okay. Okay, perfect. Okay. So now everything is fine. Today is the first class on Newton's laws of motion. So we're starting chapter 4. This is the introduction to dynamics. So basically, so far we dealt with kinematics. Kinematics, the goal was just to describe a motion without thinking about forces or other effects that generated that motion. Now we're going to talk about forces. So dynamics is practically almost every mechanical device that you see around us, and practically starting from vehicles and ending with the keyboards of computers, everything has some mechanical system or subsystem. And what is interesting is that the behavior of any mechanical system can be analyzed, can be completely understood only in terms of two basic principles, maybe three. Okay, three basic principles. And those basic principles are second and third Newton's law of motion, and after that, Newton's law of motion for rotations. So if we understand those three principles, in general, everything else is, everything mechanical is going to work. We can design it, we can analyze it, we can make it work. Okay, so Newton's three laws of motion. The first law of motion says that if an object is in a state of rest, that object is going to stay in a state of rest until an external force changes that state of rest. If an object is in a state of motion, and there are no external forces acting on that object is going to keep moving with the same velocity along a straight line forever until some external force appears and changes that state of motion. So this is Newton's first law. And you're going to actually, we used Newton's first law. If you remember, when we analyzed the motion of a projectile, we said that in horizontal direction, there are no forces acting on a projectile. If there is no air resistance, there are no forces acting in horizontal direction. And therefore, the velocity, the horizontal component of velocity of the object never changes until the object hits the ground and the collision between ground and the object changes the velocity. So we used, and this first law is easy to understand, but sometimes it is surprising. For example, why do we need seat belts in vehicles? Well, the reason is that in general, vehicle is moving with certain velocity, and if there is a sudden stop of the vehicle, your body continues its state of motion with the same velocity as the car had before this sudden stop. So your body would continue, and if there were no seat belt, your body would go through the windshield, keep its velocity in forward direction until you hit the ground. So this is one example. Another example related with circular motion is that, well, imagine that again you're driving a vehicle with relatively high speed and you make a sharp turn, let's say to the left. What is going to happen? Well, the vehicle is going to turn because the wheels and tires and the forces between the pavement and the tires make the vehicle turn. However, your body wants to keep moving along a straight line with constant velocity. The same way, this is what Newton's first law says. And you feel that even though the car is turning to the left, you feel like compared with the car, you feel that your body wants to go to the right, to the opposite side. In reality, your body wants to go along a straight line with constant velocity. And there are many other examples that we can talk about. You're going to see that Newton's first law actually is a special case of Newton's second law. And Newton's second law contains the essence of dynamics. Newton's second law says the following thing. If you have an object with mass m, the product of the mass of that object times the acceleration of that object is equal to the net force acting on that object. Here, by net force, we understand the net force is the vector sum of all forces that act on that object. So F1 plus F2 plus so on if you have multiple forces. It is a vector sum. So this is the basic law, and practically every single problem that doesn't involve rotations is solved by applying Newton's second law, this simple equation. Notice that that simple equation is a vector equation. So it can be written in components. So you have mass times acceleration x component is equal to net force x component. You have mass times acceleration y component is equal to net force y component, and z component if z component is necessary also. But in general, even though it is a vector equation with components, it is a relatively simple expression. So now we have to figure out what is the meaning of the three variables that enter Newton's second law. So mass first. What is a mass? Well, exactly like in mathematics, in any branch of science, you have terms that cannot be defined using previous knowledge. So mass is something that everybody kind of understands what it is, but we can, strictly speaking, we cannot define the concept of mass. Well, actually, there are two separate ways the concept of mass appears in science. The first way is in Newton's second law, what you see on the board. So basically, mass is, from Newton's second law, it kind of describes the tendency of objects to keep their state of motion or state of rest. So objects kind of resist to changing their state of motion, to changing their velocity. And the degree of that resistance is one way to measure a mass. So in SI units, mass is measured in kilograms. It is a little bit, 1 kilogram is a little bit of 2 pounds. But mass is not weight. This is a completely different, the weight of an object is something completely different from mass. Well, there is a relation between them, but we shouldn't make a mistake. In SI units, it is kilograms, and of course, the kilogram is one of the 7 basic units in SI units. So there is a echelon for mass somewhere in France that is kept under special conditions, and this is our unit of mass. There is a second place where the concept of mass appears completely in a separate way. And we're going to talk about that second way to interpret mass when we start talking about gravitational force, hopefully sometimes around the end of the class today. Now, acceleration, the second variable in Newton's second law, is something that we analyzed. It is the change of velocity per unit time, or the rate of change of velocity. Now, what is force? Force is another fundamental concept that we, strictly speaking, again, we cannot define strictly because it is fundamental. But we understand force either as a push or a pull. Well, if we use a definition of mass based on this gravitational force that I'm going to talk about sometime in the next several minutes, in that case, in Newton's second law, only the net force is something that we don't know, strictly speaking, how to define. In a sense, we can interpret Newton's second law as a definition of mass. So we can say, well, as a definition of force, we can say the product of a mass of an object multiplied by its acceleration is what we call net force. So a force is a vector quantity. It has magnitude, and it has also direction. And in addition to that, forces also have application points. So in many cases, we're not allowed to use different representatives of a free vector for the force, because a force applied to this spot acts differently than the force applied to the same object, but on a different point. So application points of forces are going to become important in chapter 5 when we deal with rotations. Okay, so mass is measured in kilograms. Of course, acceleration in magnitude, it is measured in meters per second squared. And therefore, the unit for force is what? Kilogram times meter divided by second squared. This is the unit for force. And that unit has a shorter name. It is called Newton. So 1 Newton is 1 kilogram times 1 meter divided by 1 second squared. 1 Newton is approximately 1/4 of the weight of an object that is 1 pound. Also, 1 Newton is about well, about 9.8, 9.8 of a kilogram, of a weight of a kilogram, object with a mass 1 kilogram. Okay, so here, well, I set up this nice table.
Hold on one sec.
Yes.
Let me get a video going.
Okay.
Let's see here.
So you're switching to,
Yeah.
let's see. Let's see if this is going to work. Well, if you have worked in a restaurant, here is one way to change the tablecloth. You see that the objects on top of the tablecloth didn't change much their position. Why? Because they contain this property that we call inertia. Because they're massive objects, and massive objects have this property called inertia. They want to keep their state of rest, or if they were moving, their state of motion with constant velocity. So were those objects moving before I pulled the tablecloth? Yeah, they were not moving, but keep in mind that the planet Earth, together with the entire solar system, is orbiting the Milky Way galaxy with a speed of the order of a little bit more than 200 kilometers per second. So every second, 200 kilometers. 200 kilometers is the distance from here to Bozeman, Montana, right? Or to Salt Lake City. So every second, the planet Earth, together with all those tables and everything else, is moving with that speed. And those objects want to keep their state of motion with 200 kilometers per second along a straight line, well, along the orbit of the solar system. Okay. So this is Newton's second law. And the last piece, the last concept that we need in order any mechanical device to work is Newton's third law. And you have heard about Newton's third law. It is the so-called action-reaction law. It says that if one object acts on another object with certain force, the second object acts on the first one with the same force in magnitude, but in opposite direction, a reaction force in opposite direction. So it sounds, well, it sounds a little bit not important. But in reality, you need Newton's third law in order, for example, to make sure that jet engine works, or to make sure that certain part of a mechanical device doesn't break. So here is an example of Newton's third law, the action-reaction law. If I apply a force on the wall, the wall simultaneously applies a force to my body. Exactly the same force in magnitude, but in opposite direction. Well, I clearly cannot move the wall, but if I were standing on ice, for example, and I push the wall, you're going to see that the reaction force from the wall on my body is going to push me in opposite direction. So this is the meaning of action-reaction law. And you can demonstrate a little bit later that Newton's third law, the action-reaction law, is equivalent to something that we call conservation of linear momentum. One of the 4 basic conservation laws of nature. So knowing those 3 Newton's laws, actually we need only 2 of them, we can solve any problem, we can design any device we want, and we're going to be sure that that device is going to work. Now, look, notice why do we need only 2 of the 3 Newton's laws? Why the first law is not fundamental? Well, if you look at the second law, you are going to see why. So if the net force acting on an object is 0, well, this means that mass times acceleration is 0. In other words, either the mass of an object or the acceleration of the object should be 0. By definition, masses are non-negative numbers. They cannot be negative, and actually they cannot also be 0 in classical context. So if we say that the net force acts on an object is 0, this immediately implies that the acceleration of that object is 0. Well, 0 acceleration means that the object is moving with constant velocity along a straight line, and this is exactly what Newton's first law says. And of course, the opposite is also true. 0 acceleration immediately leads to the fact that the net force acting on an object is 0. Okay, now we talked about different forces, but now we have to give examples with the most common forces that occur in nature. Let me look what the order of those forces is. Okay, let's start with the gravitational force. Right? Gravitational force is what makes this piece of chalk accelerate in downward direction with acceleration 9.8. So the gravitational force was again discovered by Newton. And it is a simple expression which says that if you have one object, and for simplicity, we're going to consider those objects as point-like objects, very small compared with the distance between them. So if you have one object right here with mass m1, and if you have another object somewhere here with mass m2, and if the distance between the 2 objects is r, Newton's law of gravitation, a fundamental law of nature, says that there is an attractive force, attractive gravitational force appearing between those 2 objects, and the magnitude of that force is given by a constant, gravitational constant, capital G, times the product of the 2 masses divided by the square of the distance between them. Fundamental law of nature. So what does fundamental mean? Means that, well, depending upon how you count it, the entire universe, so far we have observed only 4 types of forces, or 3, or even 2. And the gravitational force is one of those 4 fundamental forces. Now, Newton's law of gravitation, written the way I have written it on the board, gives you only the magnitude of the gravitational force. the direction of the gravitational force is such that the gravitational force is attractive force. So the gravitational force acts on the first object, but exactly the same gravitational force in magnitude acts on the second object. So the planet Earth attracts my body to the center of the planet Earth. So if I don't have a firm floor, I'm going to fall. Exactly the same way, my body is attracting the planet Earth to the center of my body. Of course, the planet Earth doesn't move much, and because its mass is very large. So again, Newton's law of gravitation is one of the 4 forces that govern the entire universe. And actually, even though it was the first force that was described quantitatively by Newton with this formula, even though it was the first force, it is still not quite well understood. And the reason for that is that the gravitational force appears to be difficult to quantize, difficult to describe in the terms of quantum mechanics. Actually, people have been trying to quantize the gravitational force for more than a century now, and so far, no success. The other 3 forces are quantized, so we know how they work when they appear between very small objects, when the rules of quantum mechanics are in force. Okay, so in the Newton's law of gravitation, you see that you have the gravitational constant G. And this is one of the 3 fundamental constants in nature. The other 2 are the speed of light, and the third one is which one? Planck's constant. So the speed of light appears as a fundamental constant of nature due to relativity. Planck's constant appears due to quantum mechanics, and the gravitational constant is only due to the gravity, or general relativity in a sense. So you have completely 3 separate theories describing how the nature works, and this simple expression, Newton's law of gravitation, is one of those 3 fundamental laws of nature. The value of the Newton's gravitational constant G is 6.67 times 10 to the negative 11 appropriate units. You don't need to memorize, of course, the numbers. They're always going to be provided for you. The units for the gravitational constant are such that, well, what are they? So gravitational constant is measured in Newton divided by kilograms squared and multiplied by meters squared. This is the unit in SI units, and this is its value. Okay, let's see something else. Let's apply Newton's law of gravitation for the case when one of the objects is the planet Earth, and the other object could be any object that is close to the surface of the planet. So here is the planet Earth. So here is the planet Earth, and here is an object, maybe this piece of chalk, maybe something else. So according to Newton's law of gravitation, if the mass of the object is lowercase m, and if the mass of the Earth is capital M, the gravitational force that acts on the small mass is going to be this way, and is going to have magnitude equal to gravitational constant times the mass of the planet Earth times the mass of your smaller object, divided by the distance between them. Now, what is the distance between the planet and this small object? Well, since the planet is spherical, we have to use as a distance between the two objects, the distance between the center of the planet Earth and the object. So this is the distance r that enters Newton's law of gravitation. Now, we're talking about objects that are relatively close to the surface of the planet. Right? This piece of chalk, my body, your body, we're relatively close to the surface. Well, in this case, this means that the distance to the center of Earth, the distance r, is equal to the radius of the planet Earth, capital R, plus, well, plus some height, h, the height of the object above the surface of the planet. Now, look at the numbers. The radius of the planet Earth, it is about 6,300 and something kilometers. So this is approximately 6,800, let's say 40 kilometers. While since the small object is close to the surface, this distance h is of the order of meters. In other words, it is thousands of times smaller than the radius of the planet Earth. As a result, we can approximate the distance lowercase r with the radius of the planet Earth, 6,840 something kilometers. And in this case, look what happens. Newton's law of gravitation, in that case, becomes gravitational constant, the mass of the planet Earth, divided by the radius of the planet Earth, and all of this multiplied by the mass of your small object. Now, gravitational constant is a constant, right? The mass of the planet Earth is another constant. I don't remember its numerical value, but it is given on the cover of your book or on Google or wherever you want it. So it is another constant. The radius of the planet Earth is also constant. So you have a product and the ratio of constants. When you do the multiplication division, you're going to get another constant. The value, the numerical value of that other constant is what? Well, you can guess it. It is 9.8. And the units, the right units are meters per second squared. In other words, an object that is close to the surface of the planet Earth experiences a gravitational force equal to 9.8 times the mass of that object. Well, of course, this approximation only works if you are close to the surface of the planet Earth. If you are somewhere close to the surface of a different planet, instead of 9.8, you're going to have a different number. Also, if you are flying very high above the surface of the planet, in that case, instead of 9.8, the value of the constant here in front of the mass is going to be a little bit smaller, depending upon how much farther from the surface you are located. But in general, the gravitational force that is acting on any object close to the surface of the planet is just a product of the mass of that object times 9.8. Okay, so the gravitational force, you understand, it is important because it is a force that we feel all the time. Sometimes it is useful, sometimes not quite. Now, what is the origin of the gravitational attraction between two objects? Well, this is a question that we still don't completely understand. And even Newton, when he formulated his law of gravitation, this important law of gravitation, he was able to calculate the orbits of the planets, the moon, the tides, very important calculations, with practical importance. But he refused to speculate what is the origin of the gravitational force. And he was smart because we still don't understand that origin completely. So according to the theory of general relativity, any object distorts the space-time around it. And this distortion generates what we interpret as a gravitational force. Unfortunately, the laws of quantum mechanics are not quite consistent with this type of interpretation. So at least one of those two theories is not complete because of this lack of consistency. Okay, so this piece of chalk is subject to gravitational force this way. But at the same time, the planet Earth also feels exactly the same force in magnitude in direction to this piece of chalk. Well, of course, if I let the piece of chalk go, it is going to go and hit the surface. Why doesn't the planet accelerate in direction to the piece of chalk if it feels exactly the same force? Well, the reason is that, well, Newton's second law, of course. The mass of the planet is very large. When you apply this gravitational force to the planet, which that gravitational force may be 1/10 of a Newton. So large, very large number times acceleration gives you 1/10 of a Newton. Therefore, the acceleration is going to be some very small number. So in magnitude, the acceleration is going to be, in magnitude, it is going to be this force, which is 1/10 of a Newton, divided by the mass of the planet Earth, which is large, of the order of 10 to the 34. So small number f divided by very large number is going to give you an acceleration that is really very small. And this is why we cannot detect it. We cannot. We don't see the planet Earth accelerating in direction to the chalk. Okay, another example. We have, let's say, okay, we have two people at least here in the classroom. So according to the law of gravitation, there is an attractive force between those two objects. Do you feel it? Do you feel attractive force? Do you? Why not? Maybe Newton's law of gravitation is not quite right. What's going on?
So just because it's so small, we can't feel it?
It is really so very small, because the gravitational constant capital G is of the order of 10 to the negative 11. So this is 1/100th of a billionth, a small number. So there is an attractive force acting on your body in that direction, gravitational attractive force. But since it is small, there are many other forces that act on your body that are much larger. For example, air resistance, electromagnetic, electrostatic forces. And as a result, you do not collide. So we have to be grateful that the gravitational constant is so small. Otherwise, we're all going to bump to each other all the time. Okay, so this is the first force. The gravitational force is the first force that we need in order to analyze dynamics of different systems, analyze how objects move. We need a few more forces, and probably the other, apart from the gravitational force, another very common force is the normal force, so-called normal force. It is something very simple. Here is the table, and on the surface, I place an object on the surface of this table. This object feels the gravitational force. This object has certain weight. So that weight acts in direction down to the center of the planet. However, the interaction between the table surface and this remote control, that interaction generates a force, a contact force, that is directed in direction opposite to the gravitational force and matches exactly its magnitude. As a result, the two forces that act on this remote control, the gravitational force this way and the normal force in opposite direction, well, two vectors with equal magnitudes in opposite directions, they cancel out. The result, net force acting on the remote control is 0, and that remote control doesn't accelerate, doesn't move. It stays at rest because the normal force cancels out the gravitational force. So we call the normal force normal because it is perpendicular to the surface. So you have to understand this. If you have a surface and an object like that remote control, the contact between those two objects can generate two different forces. One of those two forces is the normal force, and the normal force is always perpendicular to the surface of the contact. So usually the notation is F normal, like this. Always perpendicular to the surface of the contact. And of course, in the case of this remote control, we had the gravitational force mg, where m is the mass of the remote control acting in downward direction. The two forces have exactly the same magnitude, opposite directions, and as a result, they cancel out. In other words, the net force acting on the object is zero, and therefore the object has zero acceleration, doesn't accelerate, doesn't move. Or if it is moving, it should be moving with constant velocity, no acceleration. The diagram that you see here on the board is so-called free body diagram. So in those diagrams, we don't pay attention to the shape of the object. We think of the object exactly like before as a point. And the forces are applied to that point. Usually the point is at the center of mass or the center of the geometrical center of the object. So free body diagram is going to be something that is going to be needed when we're analyzing practically any dynamics problem. And also statics problems that you're going to encounter later on. One more thing about the normal force. Unlike the gravitational force, the normal force is not a fundamental force of nature. The normal force is a result mostly of electromagnetic interactions between the molecules of the remote control in this case and the molecules of the surface of the table. Electromagnetic interaction mostly between them. So it is not fundamental, while the gravitational force is one of the four fundamental forces. Okay, now one tricky concept. The concept of apparent weight. It is really tricky concept, and it needs a little bit of attention because there are multiple conceptual questions based on apparent weight that you're going to encounter, no matter if you're taking MCAT or not. Now, as I'm standing here, I'm standing here on the floor, I feel the gravitational force acting on my body. But what I feel is not exactly the gravitational force. I feel the contact between my body and the floor. I feel the normal force from this contact. Now imagine that instead of standing on the floor of this room, you are standing on the floor of an elevator, somewhere on the 120th floor of a building somewhere. And imagine what you would feel if the cable on which this elevator is hanging is cut. What's going to happen? Well, the entire elevator is going to start accelerating in downward direction. Acceleration 9.8, no air resistance, let's say. But your body is also going to accelerate with acceleration 9.8. This means that you do not have to touch the floor of this falling elevator in order to practically to be at the same distance from the floor. You don't need to touch it. You're going to keep falling together with the elevator. Your personal feeling is going to be of weightlessness during this process of free fall. So in reality, you're not weightless. You are subject to exactly the same gravitational force. You didn't lose your weight. Just what is lost is the normal force. You do not need to touch the floor of the elevator and you don't feel it. If you touch it very slightly, you don't feel the pressure. And as a result, you don't feel your own weight. You feel weightless. Okay, so let's analyze this apparent weight phenomenon from the point for the general case. Okay, the gravitational force, we said, that acts on any object close to the surface of the planet is the product of the mass of that object times 9.8. And consider the following situation. Here is again the floor of our elevator. The floor of our elevator. And here is you standing on the floor. Let's introduce a coordinate system. We need only y-axis. Let's choose the y-axis to point positive direction to point in downward direction. The first case, when the elevator is at rest, what is happening in that case? In that case, you have two forces acting on you. Normal force from the contact of your feet with the floor of the elevator, and you have your own weight, the gravitational force, mg. You're at rest. Therefore, your acceleration, so constantly at rest, your acceleration is 0. And now let's apply Newton's second law to your own body. The mass of your body multiplied by its acceleration should be equal to the net force. Well, in our case, the net force is mg in positive direction, normal force in negative direction because of my choice of coordinate system. But acceleration is 0 if you're at rest constantly. If this is 0, it follows that the right-hand side of the equation also must be 0. And therefore, the normal force is exactly equal in magnitude to the weight, to the gravitational force mg, to your weight. So in this situation, you feel your normal weight because what you feel is the normal force, and it happens to be exactly your normal weight, your usual weight. how would this change if the elevator is moving with constant velocity? So now constant velocity of the elevator, together with your body, of course. V is constant. What would be the acceleration of your body in the elevator? The acceleration would be 0. And therefore, again, the same Newton's second law is going to lead normal force equal to mg, and you're going to feel your usual weight. No surprise. But now look how the things are going to change if the elevator, together with your body, is going down with certain acceleration. So let's now have a different case. Now, the floor of the elevator, your body is moving, but, well, it could be not, it doesn't matter if it moves or not, but it is accelerating. With acceleration, let's say in downward direction, like this. So maybe, well, maybe the elevator is picking up speed in downward direction, for example. Let's see what would be the weight that you feel. What would be your apparent weight? Well, we have to apply exactly the same procedure. So mass times the acceleration of your body, and we said the acceleration of your body is certain acceleration, let's say 3 meters per second squared, let's say. In downward direction, so it is positive, should be equal to the net force. And in this case, the net force is going to be mg in positive direction and normal force in negative direction. The weight that you feel, your apparent weight, is going to be the normal force. Let's solve this equation for the normal force. You're going to get the normal force is equal to mg minus ma. Well, for our particular case, if you factor out your body mass, let's say 60 kilograms, you're going to have G 9.8 minus A. In other words, you're going to have M times 9.8 minus 3 is 6.8. This is your apparent weight. This is what you're going to feel. And therefore, instead of feeling M times 9.8, you feel M times 6.8, smaller force. You feel lighter when the elevator is accelerating in downward direction. You have probably noticed it if you're careful. Now, the opposite situation. Now, let's say that the elevator is picking up speed in upward direction, let's say. In other words, let's say that the acceleration of this elevator now is directed upward, picking up speed in upward direction, for example. In this coordinate system, the acceleration in that case would be negative 3 meters per second squared. So A would be negative, and with another positive sign, you're going to get plus. And you're going to get that your apparent weight, which is the normal force, is going to be m times 12.8. In other words, you're going to feel heavier. Your apparent weight is going to be larger than your usual weight. This is when the elevator is accelerating with acceleration in upward direction. And there are two more cases that you can consider. What matters is, well, in the case of apparent weight, what matters is two things. First, you have to understand that apparent weight is actually the normal force that acts on your body from the floor. And second, you have to understand that the direction of motion doesn't matter. You may be moving up or down or not moving at all. What matters is the direction of acceleration. When the acceleration happens to be upwards, your apparent weight is going to be larger. When the acceleration is downwards, your apparent weight is going to be smaller than your usual weight. So you have to play around, and in the homework assignment on chapter 4, there are some conceptual questions like that. And later on, when we get ready for the second midterm, I'm going to have a practice test that is going to include questions related with apparent weight.
So we had some requests for doing number 11 and 14
Okay.
on the homework. If we have time for that.
Can we go over problem 11 on homework 3? Homework 3, problem 11. The homework is due tonight, right? Have you solved that problem? You have? What about you? Did you solve problem 11? This is the problem with the airplane that is flying either this way or this way. Okay. Okay, we have about 5 more minutes. Problem 11, let's do problem 11 from chapter 3. And we barely have time. So you have to look at the problem. If you're online, you have to open the WebAssign and look at problem 11. But basically the problem, part A says the following thing. You have a plane that is flying in direction with velocity that is at certain angle theta above the horizontal. So the initial velocity of the plane is like this. And at that moment, this means the plane together with everything in this plane is with this initial velocity. At certain moment, that plane drops a projectile, a fuel tank. And that fuel tank, of course, has the same initial velocity like the plane at the initial moment of time, but later on, it moves along certain curve, parabolic curve, and hits the ground. You are given the initial velocity of the projectile, which is the same as the initial velocity of the plane. You are given the angle above the horizontal, the direction of that initial velocity. You are given also the height above the ground that the launch point is. So that height, let's say, is certain height h, several kilometers or some number of meters. You're asked to find the final velocity of that projectile just before it hits the ground. So the final velocity of that projectile is going to be some vector tangential to the parabola. And that vector, final velocity vector, is going to have horizontal component and vertical component also. So Vx and Vy. The coordinate system I would use is a coordinate system that has positive direction, positive y-axis down, x-axis to the right, and the origin of the coordinate system is at the launch point. So the problem is asking us to find the final velocity in magnitude. And look, to find the final velocity in magnitude, you need to know the components of the final velocity, the x and the y component of the final velocity. Well, the x component of the final velocity is exactly the same as the x component of initial velocity. In other words, here is the initial velocity vector decomposed to y component and x component. From the diagram, you see that initial velocity x component is the launch velocity v naught multiplied by cosine of the angle that they give you. So this is this component of velocity, the x component doesn't change, and it has this numerical value all the time, including at the final moment of the flight. Now the question is to figure out the y component of final velocity. For this, you have to figure out what you know about the y components. Well, you see from the diagram that initial velocity y component is equal to launch velocity multiplied by the sine of the angle that they give you. So this is one number that you know. Another number that you know is that the acceleration due to gravity is the acceleration of your, is the y component of acceleration of your fuel tank. So it is, in this coordinate system, it is plus 9.8. And you know another number. The displacement of this fuel tank, the displacement of this projectile, is the vector that connects the initial, the launch point, with the final point. And that displacement vector has y component exactly equal to the height, the height of the launch, which is given. So it is whatever number you have for your version, this is what the y component of the displacement is. In other words, for the y component, we know our three numbers, and we can find everything, including the final velocity y component. We need to use a formula that doesn't include the time of flight. And the formula that doesn't include the time of flight is Vy squared is equal to V naught y squared plus 2 times acceleration displacement. For our case, acceleration is positive 9.8. Initial velocity y component is V naught times sine, this number. So you just have to add those two terms and you can get the value. So you're going to get something like this: V naught squared sine squared of theta plus 2 times g times the height h. This is the square of the final velocity. So now we have the x component of final velocity. We just found the y component of final velocity. The magnitude of the final velocity from the Pythagorean theorem is square root of vx squared plus vy squared. In other words, it is, I'll write it right here, final velocity square root of Vx squared is V naught squared cosine squared of theta. And Vy squared is this expression. V naught squared sine squared of theta plus 2 times GH. Everything here is under the square root. This is the magnitude of the final velocity of this fuel tank. How to find the angle of this final velocity with respect to the horizontal? Well, that angle on the diagram is here, angle alpha. And we can form any trigonometric function we want to find the angle alpha. So you can say that the tangent of the angle alpha that you're looking for is opposite side, which is Vy, divided by adjacent side, which is Vx. And therefore, well, Vy was what? It was this expression, but I have to take it under square root. So it is square root of V naught squared sine squared plus 2gh. And Vx is V naught cosine. So this is the tangent of the angle that we're looking for. And therefore, the angle itself, the angle alpha, is inverse tangent of that expression. Square root of V naught squared sine squared of theta plus 2gh, all of this divided by V naught cosine of theta. So the tangent, the inverse tangent has to act on this entire expression. So this is going to give you the angle. Weber sine, I think, wants the angle in degree. So make sure that your calculator is set for degree. Well, to figure out part B of this problem, look, let's continue with part A, with this plane. If you continue this horizontal line, when this projectile happens to be exactly at the launch height, its velocity is going to be tangential, like this, to the parabola. And the angle of this velocity, because of the symmetries of the projectile motion, is exactly going to be angle theta, exactly the launch angle, but now under the horizontal instead of above the horizontal. And look, also, this final velocity in magnitude would exactly be equal to the initial velocity. Well, this is exactly the situation of the second plane. The second plane, they say it is flying this way, below the horizontal, the same angle, but with the same speed. In other words, the projectile dropped at that moment is exactly going to continue exactly along the same parabola, and it is going to hit the ground exactly with the same speed, like if it is launched this way. When you look again at the conceptual question that they tell you to review, immediately becomes clear that the second plane, the second projectile is going to have exactly the same final velocity in magnitude and in direction. So whatever answers you got for part A, exactly the same answers are going to be for part B. So let's see questions.
So another question I had is if all the exams are going to be take-homes, including the final, or haven't been decided.
The question is, are all exams going to be take-home? And the answer is no. At the moment when it is safe to have a normal exam, we're going to have a normal exam in a classroom with proctors, and so on. So use the opportunity now with this take-home exam, you to get comfortable with the type of problems that, to write actually the solutions, because the answers are given to you. To write the solutions in a proper, organized, clear way, so that when we have a normal midterm or a final, you to do very well. Hopefully everybody to finish with an excellent grade.
Is the final comprehensive?
Is the final exam comprehensive? Yes, it is. It has to include all the 14, 15 chapters that we're going to cover. So this is why keep good notes of all problems that you solve, because some of those problems are going to show up again on the final exam. So some problems from the practice tests, from the homework assignments are going to come again for the final exam. Other questions? Questions? Okay, so please don't forget to put yourself a brownie point, both of you, for today's class, because you were part of the demonstration of gravity, attractive forces. Make sure to add one additional brownie point next to your name. And we're going to talk again on Thursday. On Thursday, we're going to finish the chapter. So on Thursday, I expect you to have questions about the homework problems. If you don't have questions, I have quiz questions, I have examples in my notes. We're going to deal with them. If you have questions, we're going to answer those questions.
What about the practice exam?
The practice exam is your first midterm exam. So I sent an email to everybody. Make sure that you solve every problem. The calculational problems show well-written solution, well-organized, clear, and logical solution. The way we solve problems here in class. So solve them on a piece of paper, calculational problem, each problem on a separate page. And after that, scan those papers and email them to me with the subject line MT1. And this is going to be the first midterm. I'm going to grade it. Actually, graders are going to grade it. And since the answers are given, the midterm is going to be graded for clarity and logic of your solutions. Are the diagrams well shown with coordinate systems, velocity tangential to trajectories, and all the details that we follow here in class? And hopefully everybody is going to get a maximum grade for this midterm.
Was that a MT1 or was that NT?
MT, midterm one, MT1, subject line MT. Yes. Okay, other questions? If somebody didn't get my email about this midterm, please send me an email, and I'm going to answer with all the details that I just stated about the midterm. The midterm is due on Friday. So you're free to use tutors, any help you find. You can work with classmates, of course, keep social distancing. You can use textbooks, notes, any other materials that you find useful. And of course, no time limit, except that on Friday, you have to return the test on Friday. Okay, let's end it here. And thank you for